Now begins our lecture on graphical displays. We're going to cover chapters 10 and 11 in these next set of lectures. As an introduction, let's look at an example. The following is a bar chart. What makes this bar chart misleading? Notice what's on the vertical axis, the interest rate. And on the horizontal axis are the labels, the names of banks. So it looks like some sort of credit offering offered by each bank. It looks like Household Bank's interest rate is about 5 times as big as that of Choice Visa, or maybe 6 times as big. However, is it really that many times larger? No. The vertical axis starts at 15%, which distorts our comparison. So the vertical axis starts at 15 when it should start at 0. Which distorts our comparisons. Hopefully by the end of us discussing graphical displays, you'll be keenly aware of some of these pitfalls to avoid. So for data to be useful, we need to summarize it, either numerically or graphically or both. Tables are an obvious way to summarize data, but are often too hard to read. Consider the following 2 tabular summaries of unemployment data. This first one is the unemployment rate for high school grads. Notice that we're showing the unemployment rate from the years 1992 up through the end of 2006 and the beginning of 2007. And then within each year, we try to show it each month. It's difficult to see patterns in this table because there are so many numbers. We kind of get a good feel for the numbers. The highest it looks like it goes are in the 6s and the lowest in the 4s. Let's take a look at the next tabular display. This one is the unemployment rate for college graduates. Notice that the numbers do appear a little bit lower. The highest are in the 3s and the lowest are in the 1s. This is over the same date range, but it would still be difficult to draw concrete conclusions just based on glancing at these data. Is it easy to see patterns or trends? It's really not that easy to see patterns and trends in just the data. So let's take a look at a graphical display. Here we have a line chart. What are we looking at on this line chart? We have 2 lines. The key at the top tells us that blue is for high school graduates and the pink line is for college graduates. We see on the horizontal axis the years go from 1992 up through 2007. It's depicting the data we just looked at in the 2 tables in a very concise way. The vertical axis is the percent, and the title clearly tells us it's the annual unemployment rates. Notice that we've collapsed each year down into one data point. So for 1992, we have 1 data point for high school grads and 1 data point for college grads. Now we can see details on the trends in these data and draw some conclusions. We can see that even though unemployment looks like it tends to fall together and rise together, consistently the blue line is higher than the pink line. What does that mean? That means that high school grads over these time periods consistently had a higher unemployment rate than college grads did. So as you can see, a graphical display done correctly, a picture is worth 1,000 words. So this is a line graph or line chart, whichever one you want to call it. It clearly shows the trend that unemployment rate is consistently higher for those with a high school degree. Before we start looking at actual graphical displays, we need to know which type of variable we have, which type of variable we're working with sometimes in order to choose the best graphical display. So we're going to talk about types of variables. We have two main branches, categorical variables and quantitative variables. Categorical variables also have two subcategories. These are either nominal or ordinal. Nominal means name. So nominal variables are just the names of a category. So eye color would be the name of a category. Blue, brown, hazel, green. Ordinal categorical variables have a natural ordering to them. Notice there's no natural ordering to the eye color categories. Ordinal variables have a natural ordering, but they're still categorical, meaning they're just categories. They're just the names of categories. An example of an ordinal random variable would be the weather. If we described it as cloudy, partly cloudy, sunny. In an ordinal scale, you still have just the names of categories, but you have more of something as you go through the categories, or less of something as you go through the categories, according to which way you labeled them. The other main category of a type of variable is a quantitative variable. Quantitative refers to quantities, that is, numbers. There are two types of quantitative variables, a discrete or a continuous. Almost all of the numerical variables that you're going to encounter this semester are continuous random variables. Think of these as all the kind of scientific measurements. Height, weight, volume, speed, time. Even if your time is measured in seconds, you might think of those as whole numbers. But you could, if you had, in theory, a good enough measuring instrument, like a digital stopwatch that went out to infinite decimal places, you could go on and on out to infinite decimal places. Time, velocity, mass, etc. Continuous random variables can be put on a continuum, meaning for any two numbers that variable can take on, there always is another number in between. So in theory, if your measuring instrument was good enough, you could go out to infinite decimal places. Discrete is a special case of a quantitative random variable. This is where you have distinct cutoffs between values. The most basic example that we have is when you're counting something, like the number of blue-eyed people in the room. So that could be 0, 1, 2, 3, etc. Notice there that there is no number between 0 and 1. You can't have a half of a person with blue eyes. So these numbers cannot be put on a continuum. There is no way to measure out to any decimal places when you're counting something. So now that we've learned some types of variables, let's talk about the distribution of a variable. The distribution of a variable tells us what values it takes and how often it takes these values. A distribution can be described by a table, graph, list, or function. Good graphical displays should be clearly labeled with a title, a general subject, label all variables, put units on it, and a key if necessary. Always identify the source of the data and do not overlabel. That's more difficult than it sounds. The first graphical display that we're going to look at is a pie chart. Pie charts show how a whole is divided into parts. It can be used to graphically represent the distribution of a categorical variable. A pie chart is simply a circle where the circle represents the whole, the 100% of the data, and the wedges within the circle represent the parts. The angle spanned by the wedge is in proportion to the percentage that that category is represented by. Now, this is a simple pie chart of the distribution of degrees for persons aged, it's off my screen, my little title, sorry about that, whatever it is. And it's fine. We all know what a pie chart is. I'm sure everybody's seen one if you went through the public school system recently anyways. So this is a pie chart. We want to warn you, be careful when using pie charts. There is a growing sentiment that pie charts are generally not considered good. Your textbook doesn't mention this, but I feel compelled to show you a couple things that I've discovered over the years. This first website is written by Steve Fenton. Now he's in the UK, so he uses a little bit different of language every now and then from us, but we can get past that. I apologize that you can't see the link to this web page on your screen, but if you Google his name at the top of the page, Steve Fenton, and pie charts are evil, you will come across this page. So he lists some ways that pie charts are not good. Argument 1 is when you're comparing individual values. The British people selected their representatives in 2009 to sit on the European Parliament. The results are displayed in this evil, horrible, and plain nasty pie chart. So as you can see, the Conservatives, it's pretty easy to see that they are the biggest, but the next three categories are not as easy to tell which one's bigger than the other. Well, if we take a look at another way to display this data, he calls it a column chart, we call it a bar chart. You can see that it's much more clear the comparisons about which party is bigger than the other. Pie charts do not lend themselves well for comparing categories, and that was their whole intended purpose. Argument 2, size matters. So he's arguing here that a little pie chart or a big pie chart, that when you make a pie chart bigger, nothing different happens. A larger chart doesn't reveal more information. It's just as useless as it was when it was tiny. However, this is not the case with the bar chart. He's saying that if you make it bigger, it makes it very much more clear, easy to see your point and make comparisons. Argument 3, comparing combined values. I'm actually going to read this one because it's quite interesting. In 2010, the people of the UK voted in the general election. The results of the election was a hung parliament, which essentially meant that no single party had an overall majority. In this scenario, the two parties with the most votes looked to the smaller parties to support them in order to have a combined majority. The long and short of this electoral scenario is that you need to do a few sums. The top two parties were the Conservative Party and the Labour Party. In third place were the Liberal Democrats. So here are the important questions that come up when this happens. Could second place party Labour team up with third place Liberal Democrats to create a combined force with more seats in the parliament than the Conservatives? Check out the pie chart and see if you can decide for yourselves. It's obviously really difficult to tell who should join up with who. You can't really see whether the combined purple and yellow slice on the left would be bigger than the blue slice on the right. In contrast, when you look at a bar chart of the data, it's quite clear to see that the Liberal Democrat Party is in quite a position of power. If they add on to either one of the bigger groups, it will create a majority. So he's got some additional arguments down here and a summary, and you can read this website if you'd like. Again, Google Steve Fenton and pie charts are evil. I've got another one to show you real quick. To access this website, just type in Oracle and pie charts are evil to get the countdown of top 10 reasons to never ever use a pie chart. So figure 1 on this one is a floating tilted 3D pie chart with shadow trying poorly to show usage statistics within a graphics application. Figure 2 shows how pie charts can be very cluttered and noisy and difficult to read. They can become cluttered way too quickly. Figure 3 shows us that they're not good for making comparisons. It's really difficult for our eyes to take in the area of a wedge and compare, for instance, these yellow wedges against each other on the 3 separate pie charts. Number 4 might be my favorite, the best use of a pie chart I've found yet. Yellow in the key says looks like Pac-Man, and black in the key says does not look like Pac-Man. Alright, and figure 5 is a screenshot of a new iPad showcasing pie charts. So here we get to the countdown. Number 10, pie charts just don't work when comparing data. Number 9, you have a better option, the sorted horizontal bar chart. Number 8, the pie chart is always round. Number 7, some genius will make it 3D. Number 6, legends and labels are hard to align and read. Number 5, nobody has ever made a critical decision using a pie chart. Number 4, it doesn't scale well to more than 2 items. Number 3, a pie chart causes distortions and errors. Number 2, everyone else uses them, debunking the urban legend of pie charts. Number 1, pie charts make you look stupid and lazy. Ouch. We like to represent the truth in this course, and this is the truth. So try to avoid pie charts as much as possible. Sometimes your boss or your teacher, instructor, professor may want you to use them, but try to stay away from them if you can.